All right, before we work the first word problem here, get in your head this. Whenever you see a rate for these problems, you're going to automatically think of a derivative. Whenever you see rate, you're going to automatically think of a derivative. All right, so let's look at this one. A pebble dropped into a pond causes a circular ripple. All right, so what do we have? We have a circular ripple. And what happens to that ripple? It keeps getting larger and larger if we have still water. All right, find the rate. Find the rate. So I'm going to think of a derivative there. Find the rate at which, so I need to find a rate. I need to find a derivative here. Which derivative, you might ask? Find the rate at which the radius of the ripple is changing at a time. So I'm looking for the change in the radius with respect to time. They want me to find this. That's unknown. Okay, find the rate at which the radius of the ripple is changing at a time when the radius is 1 foot. So when the radius is 1 foot. So I'm going to put a vertical bar, and I'm going to put whenever r is equal to 1 foot in here. When the radius is 1 foot and the area enclosed by the ripple is increasing at a rate of 4 square feet per second. Look at that last part. When the radius is 1 foot and the area enclosed by the ripple is increasing at a what? At a rate. What is increasing at a rate? The area, right? So that's going to be the derivative of the area, dA, with respect to time. Okay? Derivative of area with respect to time. And what are they saying? It's increasing at a rate of 4 square feet per second. So what are they saying? The area, the derivative of area with respect to time is 4 square feet per second. All right, so let's figure out what I need to do here. I need to find dr over dt, right? I'm given dA over dt. So I know I'm going to take a derivative of something with respect to t. But I need that equation. I need that something. Well, think about your formula for the area of a circle. Area is equal to pi r squared, right? The area of a circle. Now let's take the derivative of my equation now with respect to t. So I'm going to take the derivative with respect to t of a is equal to the derivative with respect to t of the other side, pi r squared. This part, I could just call that dA over dt is equal to, how about this part? Well, what's pi? Pi is just some number about 3.14, right? So if it's a constant, you pull that out and you take the derivative of the variable part. What's the derivative of r squared with respect to t? That'll be 2 times r to the first times dr over dt. All right, let me see if I can fill some stuff in now. dA over dt is 4. So right here, I'm going to call that 4. This I could call 2 pi, right? What is r? When the radius is what? 1. So I'm going to put in a 1 here. Times, how about dr over dt? Do I know that? No, that's unknown. That's what I'm trying to find. So it stays dr over dt. So that means I have 4 is equal to 2 pi times dr over dt. And if I solve for dr over dt, I'm going to have 4 over 2 pi is equal to dr over dt. Or what does that simplify to? That simplifies to dr over dt is equal to 2 over pi. And what are going to be my units here? It's going to be the units of r, because remember this is change in r with respect to time. So units in r over units of time. What is my radius measured in? Feet. It's going to be feet per what? What is my time measured in? Seconds. So what did we just find really? we just found out how fast my radius is changing at the instant whenever this radius is 1 foot. So basically like an instantaneous rate of change.